Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about electromagnetic radiations, energy of an EMR, electromagnetic spectrum and its reasons, spectroscopy and its types, colorimetry, UV visible spectroscopy, electronic transitions, terms used in UV visible spectroscopy, absorption band and its types, Beer-Lambert's law and its deviations, and last reference. So all about this UV visible spectroscope. Now friends, I will start with to introduce electromagnetic radiations. Electromagnetic radiation is a type of energy that is transmitted through space at enormous velocities. Radiant energy has wave nature and being associated with electric as well as magnetic field. These radiations are called electromagnetic radiations. Electromagnetic radiation has its origin in atomic and molecular processes. Friends, the field may be represented as electric and magnetic vectors oscillating in mutually perpendicular planes. Electric field oscillations and magnetic field oscillations, you can see the wavelength, you can see the progress, and you can see the perpendicular of magnetic field to electric field. Now friends, energy of an EMR, electromagnetic radiation. The energy of an EMR can be given by the following equation: E is equal to h nu, where E energy of radiation is Planck's constant, mu frequency of radiations. Now frequency nu, actually it is represented, but here mu c by lambda, where c velocity of light in vacuum, lambda wavelength, and hence E is equal to h nu. So E is equal to hc by lambda. Therefore, energy of radiation depends upon frequency and wavelength of radiation. Now friends, I will focus on electromagnetic spectrum. The arrangement obtained by arranging various types of electromagnetic waves or radiations in order of their increasing wavelength or decreasing frequency is called electromagnetic spectrum. Electromagnetic spectrum is divided into a number of regions, and these are artificial divisions in the sense that they have been defined slowly as a result of differences in the instrumentation required for producing and detecting radiation of given frequency range. So friend, region of electromagnetic spectrum. So friends, you can see visible spectrum, higher frequency and lower frequency near IR. So UV, ultraviolet 190 to 400 nanometer, violet 400 to 420, indigo 420 to 440 nanometer, blue 440 to 490 nanometer, green 490 to 570 nanometer, yellow 570 to 585 nanometer, orange 585 to 620 nanometer, red 620 to 780 nanometers. Now friend, spectroscopy. What is the meaning of a spectroscopy? Spectroscopy is the measurement and interpretation of electromagnetic radiation absorbed or emitted when the molecules or atoms or ions of sample move from one energy state to another energy state. So friend, types of spectroscopy: atomic spectroscopy, here the change in energy takes place at atomic level; atomic absorption spectroscopy, flame photometry; and molecular spectroscopy, here the change in energy takes place at molecular level; UV spectroscopy, colorimetry, infrared spectroscopy. So absorption spectrophotometry, spectrophotometry. Absorption spectrophotometry can be defined as the measurement of absorption of radiant energy by various substances. It involves the measurement of absorption specificity for radiant energy in the visible UV and IR region of the spectrum. So friend, colorimetry, lambda 400 to 800 nanometer, colored substance absorb light of different lambda in different manner and hence get an absorption curve. The lambda at which maximum absorption takes place is called as lambda max. The maximum is characteristic for every colored substance on plotting graph of concentration versus absorbance. We get a calibration curve that is useful to determining the concentration of amount of drug substance in the given sample solutions. You can see here the wavelength nanometer and maximum absorption at this wavelength lambda max. So UV visible spectroscopy. UV visible spectroscopy is connected with the study of absorption of UV radiation, which ranges from 200 to 400 nanometer. Valence electrons absorb the energy thereby molecules undergo transition from ground state to excited state, and this absorption is characteristic and depends on the nature of the electrons present and types of electrons. Sigma electrons in saturated compound, pi electron in unsaturated compound, and n electrons in unbonded electrons. So you can see the transition into pi star, into sigma star, pi to pi star, and sigma to sigma star. So sigma to sigma star transitions. Sigma electron from orbital is excited to corresponding anti-bonding sigma or a star orbital. The energy required is large for this transition. The organic compound in which all the valence shell electrons are involved in the formation of sigma bond do not show absorption in normal UV region. So this transition is observed with saturated compounds. Example, methane CH bond only can undergo sigma star transition and show absorption maximum at 122 nanometer. The usual spectroscopic technique cannot be used below 200 nanometer. To study this high energy transition, the entire region should be evacuated. Here the excitations occurs with net retention of electronic spin, and this region is less informative. So now pi star transition. Pi electrons in bonding orbital is excited to corresponding anti-bonding orbital pi star. Energy required is less when compared to into sigma star. Compound containing multiple bonds like alkene, alkynes, carbonyls, nitriles, aromatic compounds which undergo pi star transition. Alkene generally absorb in the region 170 to 200. Absorption usually occurs in the ordinary UV spectrophotometer. Absorption band in unconjugated alkynes and absorption band in carbonyls. Introductions of alkyl groups in olefinic linkage produce bathochromic shift. Now friend, N to pi star transition. Saturated compound containing one heteroatoms with unshared pair of electrons like oxygen, nitrogen, sulfur and halogen are capable of N to pi star transition, and this transition requires less energy than sigma star transition. In a saturated alkyl halide, the energy required for energy time decreases with increase in size of halogen atom. So friends, methyl chloride has lambda max 173 nanometer. Methyl iodide has lambda max of 258 nanometer. And this type of transition is very sensitive to hydrogen bonding. Alcohol and amines. Hydrogen bonding shift the UV visible absorption to the shorter wavelength. Nanometer into pi star transitions, an electron from non-bonding orbital is bonded to the anti-bonding pi star orbital. Compound containing double bond involved heteroatoms undergo such type of transition, and this transition requires minimum energy out of all transition and shows the absorption band at lower wavelength around the 300 nanometer. So saturated aldehyde shows both types of transition into pi star and pi star at low energy and high energy around 220 nanometer to 180 nanometer. So term used in UV visible spectroscopy. Chromophore. Chromophore is defined as the nucleus or any isolated covalently bonded groups responsible for the absorption of light radiation Any group which exhibit absorption of electromagnetic radiation in the visible or ultraviolet region. And some of important chromophores are carbonates, acid, esters, nitrites, ethylenic groups. So absorptions characteristic of some common chromophores you can see. Now oxochrome. These are coordinately saturated or unsaturated groups which themselves do not absorb radiation, but when the present along with a chromophore enhances the absorption properties of the chromophore, also known as color enhancing group. All oxochrome have one or more non-bonding pair of electrons. It extends the conjugation of chromophore by sharing the non-bonding electrons. So friend, benzene, phenol, aniline, you can see aniline 280 nanometer, 270 nanometer and 250 nanometer. Absorption and intensity shift. So bathochromic shift, red shift, when the absorption's maximum lambda max for a compound shift to longer wavelength, it is known as bathochromic shift. The effect is due to the presence of oxochrome or by charge of solvent. The N to pi star transition for carbonyl compound experience bathochromic shift when the polarity of the solvent is decreased. So hypsochromic shift, blue shift, when the absorption maxima of a compound shift to the shorter wavelength is known as hypsochromic shift or blue shift. The effect of is due to the presence of group causes removal of conjugation or by charge change of solvents. So you can see the aniline show blue shift in acidic medium since it loses conjugation in aniline and ammonium ion. Now hyperchromic shift. When the absorption intensity of a compound increases, it is known as hyperchromic shift. The introduction of oxochrome usually increases absorption intensity. You can see the pyridine 252 and 2-methylpyridine 260. Now hypochromic shift. When the absorption intensity of compound is decreased, it is known as hyperchromic shift. The introduction of group which distort the unity of molecule causes the hypochromic effect, naphthalene and 2-methylnaphthalene. Now you can see the bathochromic shift, blue shift, red shift and hyperchromic shift. So absorption bands. Formations of absorption band. The spectrum consists of sharp peaks and each peak will correspond to the promotion of electron from one energy level to another. During the promotion, the electrons move from given vibrational and rotational level within one electronic mode and other within the next electronic mode. Thus, there will be a large number of possible transitions, means not just one but a large number of wavelengths which are close enough will be absorbed, resulting in the formation of band. So types of absorption band. K band originate due to pi star transition from a compound containing a conjugated system. Such type of bands arise in compounds like diene, polyenes and enones. Now friend, R band transitions originate due to into pi star transition of a single chromophoric group and having at least one lone pair of electrons on the heteroatom. These are less intense with an Emax value below 100. Now B band, such type of band arises due to pi star transition in aromatic or heteroaromatic molecules. Benzene shows the absorption peak in between 230 to 270 nanometer when a chromophoric group is attached to the benzene. The B band are absorbed at a longer wavelength than the more intense K band. E band originate due to the electronic transition in benzenoid system of the three ethylenic bond which are in close cyclic conjugation. These are further characterized as E1 and E2 bands. E1 band which appears as shorter wavelength is usually more intense than E2 band for same compound which appears at the longer wavelength. So friends, hope this video will be helpful to you. If you like this video, then subscribe my channel and thanks for watching.